Hello, a little interruption to the ongoing series because I've been on holiday. Can you tell? Is it the shirt that gives it away? I've been to a delightful little Welsh seaside town called Conwy. It's famous for having a castle and the world's smallest house, and now that I'm a father, it has a ye olde toy shop that I was commanded to enter and go and explore. It was actually a very nice shop indeed, but I had a big hit of nostalgia when I saw this. A Spirograph kit. Now, I hadn't played with one of these since I was a child, and I was just desperate to get back to our apartment and try it out. This particular Spirograph imitates, I think, probably like the first set that was ever released. It's deliberately retro in its design, and a Spirograph fundamentally contains sort of rings and gears, and it's really good fun. Let's take out the main ring here, and we'll take out one of these smaller ones, and we'll take a pen as well whilst we can. Move this out the way. And it comes with a little pad, and it also comes with some instructions for creating nifty ideas. Let's have a go. So if I put the ring down on the pad, I think you're supposed to use some blue tack or something to hold it down, but nonetheless, I'm just going to run with it today. I've got my blue pen. We can pick a hole. As you can see, it's all a bit clumsy, a little bit fiddly, but I'm going to put the pen in the hole, and you draw around like this, and eventually you create these pretty spirals. Got to try and keep everything really steady. Don't move. Oh, no. Oh, hang on. Well, that's no good, is it? Wouldn't it be nice if there was a more reliable way to do this? Now, I have come to learn that going on holiday with young children means that the holiday evenings are not quite as exciting as they used to be, and so my brain started to try and think of ways to code a spirograph, which presented a bit of a problem. The only computer I take on holiday with me, or indeed travel anywhere with, is my trusty Chromebook. I've had this thing for years. I love it, I think it's great, and you can probably tell by the colour of it, it's been used fairly extensively. It is filthy. But if you've ever tried to do any development on a Chromebook, it's quite an underwhelming experience. They're just not kitted out for doing it. And, well, I could try and remotely log into my workstations from Wales, but I'm quite convinced that goats and sheep do make up the infrastructure of the internet in Wales. But then I remembered something. My good friend Maurice Smith here has not so quietly been working on a project in the background, and it's called PGE Tinker, Pixel Game Engine Tinker, for those that don't already know. And even though I could look at all of the code for it, it's all web stuff. I don't know any of this. And so instead, I'm going to point my browser to pgetinker.com. And isn't this neat? It's a complete Pixel Game Engine tinkering environment. It's in fact actually a C++ compilation environment that has all of the Pixel Game Engine header files and utilities available to use. Yes, you can write your code directly in the browser, click the Run button, and see what the output is. In this case, it's the Burr Pixel Game Engine program, so there's not much to see. But let's choose one of the other examples. Let's pick the PGE Classic demo. I think this is a bit more colourful. You can see it is standard Pixel Game Engine stuff. You override the engine, you provide an on-user create and an on-user update method, and other than that, it is exactly the same. There is a little trick to loading some images because you're no longer working with a local file system, but let's leave that for now. Let's click the Run button instead. And once it's compiled, you can see it looks, feels and smells like Pixel Game Engine. Isn't that nice? Well done, Maurice. And because this all runs in the browser and the heavy lifting is done by some server somewhere in the world, my little Chromebook could run it no problem at all. Once you've created your Tinker, you can click the Share button up here to get a URL, which you can then share, well, wherever you want. So let's stop this application. Let's create a new Burr OLC Pixel Game Engine application, which is really just an empty template file. For today, I'm going to get rid of this file loading specific stuff. We don't need it, and we're going to make that disappear in the future anyway. And let's use these tools to try and make a spirograph in Pixel Game Engine in the browser. As regular viewers of the channel will know, I don't like to leave anything for granted in a video. And I've done several videos that have used the mathematics of circles in the past, but let's just have a quick refresher just to make sure we're all on the same page. In 2 dimensions, we can define our circle on the XY plane. The middle of our circle is the origin. If we take a radius, r, and an angle, theta, we can work out the location of this point using the following equation. X equals r cos theta, and y equals r sine theta. If we were to start theta at 0 and step through it all the way to 2 pi, we would define all of the points on the circumference of our circle. Let's jump over to PGE Tinker and visualize this. I'm going to create a pixel game engine application that is 512 by 512 pixels with a relationship of 1:1 engine pixels to screen pixels. The Pixel Game Engine Tinker environment will scale that appropriately in this output window. I know I'm going to need a few basic things. I'm going to change my value of theta over time. Effectively, I'm going to accumulate time. And I'm going to accumulate time when the user presses the spacebar in my onUserUpdate function. I'm going to add in a little reset function, which means at any point I can go to a known state. In this case, I'm going to reset my accumulated time and just refresh the output to black. And I'll allow the user to reset whenever they press the R key. Next, I'm going to create a point that represents our pen's location on the screen. And for now, I'm going to handcraft some values. One of the cool things you'll see with PGE Tinker is it's actively compiling whilst I'm typing, so you get quite a smooth development experience. I'm just going to implement the equations we've just seen. vpen.x equals some radius, in this case 200, multiplied by cos, and I'm just going to take my accumulated time value, and I'll shift it to the middle of the screen. Y is pretty much the same, except we use sine. To avoid the drawing looking like a sequence of dots, we need to draw lots of little lines from where the pen is now to where the pen was on the previous frame. This means I need to store where the pen was on the previous frame. I'll add another member variable called oldPenPoint. And before I exit the onUserUpdate function, I'll store that pen point. Using the drawLine function, I can draw a line between those 2 points. However, what is oldPenPoint the very first time we need to use it? It's undefined. It'll give us some glitch. To deal with this, I need to understand when is the very first time I'm drawing a line. So I'll add in a flag called bFirst equals true, and I'll also add that to my reset function. So now we know that the very first time we want to draw a line as part of our circle, the old point is equal to the new point. Well, PGE Tinker says there's no errors currently, so let's run it and take a look. Well, good, we've got a black square and we've got a little white dot over here. Now, if I hold down the spacebar, we can see it drawing a circle. And if I let go, it stops drawing the circle. It only draws the circle whilst time is being allowed to progress. And if I press the R key, it resets. We are circumscribing this circle. Now, obviously, spirographs are not circles, but the trajectory of the gears are circular. Let's have a look what I mean by this. A typical spirograph contains a fixed gear. It's usually of the form of a ring-shaped disc like this. And I'm just going to put in the middle a very obvious origin point. Let's call this one the fixed gear. Now, either on the inside or the outside of the fixed gear, we have a moving gear. And these come in different diameters. Let's also put in an origin point. And we'll call this one moving gear. Despite them being gears, the path the moving gear takes is circular with respect to the fixed gear. Given that if we know the angle theta and radius r, we can calculate the midpoint's location of this moving gear with respect to the fixed gear. And hopefully you can see that the radius of that trajectory is the equivalent of the radius of the fixed gear to this inner surface minus the radius of the moving gear. Let's go and visualize this in PGE Tinker. We're going to need to add in a few more variables now. Let's start with the fixed gear radius. I'm going to set that to 200. And now the moving gear radius, which I'm going to set to 75. We can work out where the moving gear is by using the same equations before. Our r, however, has become the difference between the fixed gear radius and the moving gear radius. Let's draw these gears. We can use the draw circle function, but we'll need to define where the middle of our fixed gear is, because everything else is relative to that position. For now, I've just defined it as the middle of the screen. we did the same thing here, but manually. So I want to draw a circle of V fixed gear pos with a radius of fixed gear radius. That will draw the fixed gear. Let's also draw the moving gear. Note that when we've calculated the moving gear position, we haven't offset it from the origin. We can do that here, and this time the radius is the moving gear's radius. For the time being, we're no longer drawing a line, but let's run the script and see if our gears are behaving. Well, I can see the fixed outer gear and the moving inner gear, and if I hold down the spacebar, very nice. However, it's not erasing the previous scene. That's because we've not cleared the previous scene. I know we do in the reset function, but we should do it every loop. Let's try again one last time. Good, we've got our inner gear moving around our outer fixed gear. Gears, of course, don't just move around next to each other, they roll against each other. We can't observe that in this visualization. What we could do with is another point on this inner gear that represents where the pen will be. The pen can be offset anywhere on the radius of the moving gear, perhaps here, for example. Well, working out that location relative to the moving gear is no different to what we've already been doing. We can work out a theta and a radius. As we calculate the location of the moving gear, we incremented theta by accumulating time. The rate at which we increment this theta, let's call it theta prime, depends on the relationship of the fixed gear and the moving gear. There is some coefficient that describes that relationship, and it's called the gear ratio. Now, assuming our gears are ideal and don't have any weird wonky teeth or anything like that, and we call the radius of the fixed gear Rf, and we call the radius of the moving gear Rm, then our gear ratio is equal to Rf divided by Rm. And intuitively this makes sense. If Rf was equal to 10 and Rm was equal to 5, the moving gear would have to do 2 full rotations before it's back to where it started. So let's add in this pen offset radius. I'm going to set it to be a little bit smaller than the moving gear radius, so it's near the outer edge of the moving gear. Calculating the gear ratio is as easy as dividing the fixed gear radius by the moving gear radius. And we can calculate the offset of our pen relative to the midpoint of the moving gear by using the same equation as before. The only difference here of interest is we take into account the gear ratio, and we also invert the direction of rotation. Remember, if two gears roll against each other, one has to turn one way, forcing the other one to turn the other way. Fundamentally, our fixed gear position, our moving gear position, and our pen offset are all two-dimensional vectors now. And if we accumulate those, we can work out where our pen is relative to the fixed gear. In fact, I'm just going to draw another circle at our pen point location, so we can see this move around. I'll give it the radius of 4. Let's take a look. So we can see our fixed gear, our moving gear, and the pen point just about on the edge of the inner moving gear. And if I hold down the space bar, we can see that the pen point effectively rotates in accordance to the motion between the two gears. Now we can get to the exciting bit of actually drawing the spirograph. We just want to now draw a persistent image at that location. I'll bring back in our drawLine function and I'll just set the colour to be red. But I've got a bit of a problem. Every single frame I'm clearing the screen to black. Let's take that out. But, as you'll see, this won't be a very pleasing output. We need to make sure that the circles don't remain persistent between frames, but the red dot does. In Pixel Game Engine, there are several ways to achieve this. We could use layers. However, they're a little bit complex and perhaps not very intuitive. The easier way is to draw the debugging framework of the gears as decals, which are always drawn on top of the sprite background. So, for example, just to prove that this does start to look like a spirograph, I'm not going to draw the circles, I'll just draw the line. I'll hold down the spacebar, and we start to see what begins to look like a bit of a spirograph. They are quite hypnotic to watch. That's nice. That one goes back on itself. Look at that. Pretty. Like it. But it would be nicer to see the gears overlaid. In Pixel Game Engine land, decals are always drawn after sprites. So this draw line function is actually a sprite. That means it's updating some memory via the CPU. Decals only last that one frame. They have no persistence, so that makes it an ideal solution. However, the problem is there is no draw circle decal. Now there's a variety of reasons for that, but there just isn't. To remedy this, I'm going to add one to our example program. Now how this works isn't exactly relevant to today's video. It fundamentally consists of three components. Firstly, we've got the draw circle decal function, which takes in a position, a radius and a colour, and then goes ahead and calls the requisite Pixel Game Engine functions in decal mode to go and draw it. To save us having to calculate circle vertices all the time, using sine and cos, which could be a bit costly, I'm creating a unit circle once and then transforming it by scaling it and repositioning it as necessary. We'll see in future versions of Pixel Game Engine that these sort of things should be entirely const expression compatible. But today they are not. However, this gives us a quick and dirty draw circle decal function. This means I can bring back in my draw circle functions and replace them with draw circle decals. Let's take a look now. There we go, that looks very nice. In fact, it even looks a bit better because decals don't obey the laws of pixel sizes in the Pixel Game Engine, so it's actually using the best resolution it can. If I hold down the spacebar, we can see the circles are moving around, now drawing our nice spirograph. By changing the radii of our gears, we can affect, of course, what the spirograph looks like. That's very nice. I like this a lot. Yeah, I could watch this all day. An interesting quirk of spirographs is you may notice that they eventually line up again. They become periodic. Well, that's because there are common factors between these different radiuses. If we make it a little bit more clumsy and difficult to work with, and I'll just speed up time as well, just to make a point here, you can take advantage of aperiodicity. I'll wait for it to finish this loop, and you'll see it never quite syncs up again. It will do at some point, but maybe not for a long time. Yes, I like this a lot. The Pixel Game Engine repo consists of things other than just the header file. Now yes, we all know all you need is that header file in order to do things, but there are other things here. A lot of the videos from the One Lone Coder YouTube channel end up as extensions or utilities. A nice one we can exploit today is Quick GUI, which should allow us to make our Spirograph application a little bit more real-time interactive. Now, I'm not going to rattle through all the detail on this, there's no point, we're almost at the end, but I just wanted to demonstrate that yes, look, I've included the Quick GUI extension as part of the Tinker, and I've gone away and added some other bits of code from other projects too to make it a little more colourful. Here is the GUI stuff being added, and here is the GUI stuff being set up, but rather than talking about the code, let's just see what it does. So I'm going to click the Run button. And to make things a little more visually appealing, I'm going to click this Maximize button, and I'm going to press F11 in my browser. And we can see that we've got three circles, the pen point, the moving gear, and the fixed gear, and we've got three sliders up here. This slider adjusts the radius of the fixed gear. This slider adjusts the radius of the moving gear, and you can see we can go on the inside or the outside of the fixed gear, and this slider adjusts the offset of the pen relative to the moving gear. And we can break the laws of physics. We can do all sorts of spirographs never before seen by man. But that's enough sliding. Let's press the draw button. This is very pretty. We'll draw a little bit like this to begin with. You see the colours are changing. That's nice. We'll make it a little bit larger, and we'll put the moving gear on the outside, and we'll bring in the pen offset. Let's try that one. It's a bit of a wibbly wobbly circle on the outside there. Oh, that's nice. Let's bring it back in, and we'll have a inside big circle one. There we go, like that. And we'll have the offset not too much. Try and make this a bit more circular. Let's go. Yeah, I could play with this all day. It's very, very nice. We'll do one more. We'll just change. We'll do a physics breaking one. Let's go big circle, and we'll do something around that size for the moving gear, but we'll position the pen on the outside of the fixed circle. Let's have a look. What does that produce? Oh, that's very pretty indeed. When you're happy with your tinkers, you can of course share them to whatever forums or discords or reddits or whatever you want. And the nice thing is, once you have shared your tinker, that link is persistent. If somebody goes away and edits it, it becomes a new link, so you don't lose the work. As you can see, this is very pretty indeed now. I like this a lot. And just to annoy everybody, I'm going to stop that one there. Let's come out of PG Tinker for a moment, and I just want to show once again, thank you Morris Smith, otherwise known as Morris1138, for putting all of the effort into this fantastic project. As I said at the start, he has released all of the source code for it too, and he's maintaining quite a thorough devlog that chronicles the ups and downs of building such a project, and to some extent working with me. And so that's that. Finally, the world has a solution to a problem it didn't know it had. How do you develop Pixel Game Engine applications without a Pixel Game Engine development desktop? Well, the answer is pgetinker.com. Thank you very much, Morris. If you've enjoyed this video, a big thumbs up, please. Have a think about subscribing. Go and give Morris some support too, and I've no doubt you'll have lots of tinkers to share on the Discord. Until then, see you next time. Bye-bye.